Our final chapter for this course, chapter 14, we won't be covering the entire chapter, but sort of hitting some of the most important points that are covered in this chapter. And given what most of you are looking at in terms of future chemistry, the topic that's most important for all of you is the topic of oxidation and reduction. So I believe, mentioned these terms very, very briefly a long time ago, probably somewhere around chapter 4. And these terms, oxidation and reduction, refer specifically to a reaction where electrons are transferred. And in the first example we look at, we can see the electron transfer very easily. As we get into more complicated reactions, that'll become less and less obvious. But let's see this first example. So you can see what's happening here is that we have zinc metal, and it's reacting with a copper 2+ ion, and as a result we form a zinc 2+ ion plus copper metal. So where do we see electrons moving here? Well, if you look at the zinc is starting out neutral, but it's losing electrons. In fact, we can see specifically the zinc loses 2 electrons because it goes from neutral to a +2 charge. And so when an atom loses electrons, we say that that's being oxidized. Copper, on the other hand, you can see it starts out positively charged and ends neutral. So the copper gains 2 electrons. And when an atom gains electrons, we say that it's being reduced. And often for reactions, this one's pretty straightforward, but we divide these oxidation reduction type reactions up into half reactions. One half reaction shows the oxidation, one shows the reduction. So we can see in one half reaction we have zinc solid forming zinc 2+ plus 2 electrons. And in the other case, copper 2+ gains 2 electrons to form copper. All right, now as reactions get more complex, how do we start to find our oxidation and reduction steps, our half reactions, as well as identify the atom that's being oxidized? So here we have magnesium plus oxygen forms magnesium oxide. And it's not necessarily as obvious here where the oxidation is and where the reduction is. So the first general rule we can point to is something we already know. And that's metals we know are not very electronegative. And so metals, as we've seen many times before when they form ionic compounds, like to donate electrons. So metals are usually very easily oxidized. Whereas nonmetals, being highly electronegative, want electrons. They like to receive electrons. And so nonmetals usually are able to be reduced. So here the magnesium is reduced. I'm sorry, the magnesium is the metal. So the magnesium is oxidized, and the oxygen, being the nonmetal, is reduced. But not every reaction involves metals and nonmetals. So what do we do when it's not obvious at all? Well, in those cases, we need to do what's called calculating an oxidation number. An oxidation number is the charge that an atom would have if it were ionic. Sorry about that. I'm just having some technical difficulties here. So, as we said, the oxidation number is the charge that an atom would have if it was ionic. Doesn't mean that it is ionic, just if it were ionic. So how do we determine that? So here's how we can do that. First, an atom in its elemental state, or its natural state, always has an oxidation number of 0. So this would be something like H2 or O2 or S8. Again, it's anything that's when the element is in its natural state. Second thing that we can say about this, in any monatomic ion, charge is equal to oxidation number. So if we had a sodium plus ion, its oxidation number would be exactly what the charge is, +1. We can also make a number of judgments based on which group things are in on the periodic table. So the halogens, or group 17 for example, generally have an oxidation number of -1. Group 1 metals, such as lithium, sodium, potassium, etc., are almost always +1. Group 2 metals, such as beryllium, calcium, strontium, and so on, are +2. Hydrogen is usually +1, unless it's bonded to a metal. Then it's -1. Oxygen is usually -2. So that usually gets us about 75% of the way there. From there, we add up what we have, and then we sum up the rest, because the sum of all the oxidation numbers must equal the total charge. All right, so I'm going to stop this video for the moment, and hopefully I can get my stylus working again, and then we'll continue on with some examples.